Okay, so we can proceed now. Over to you, Razak.
Yeah,
Hey, thank you.
good afternoon, everyone. I welcome each and every one of us to another episode of Smart Conference. Um, for those that have been joining us before now, Smart Conference is a conference that brings those people that are experts on the field, that knows about the research and bringing it to reality. I welcome every one of us and I greet us, and I anticipate that we enjoy this session. So smart, this is sustainable mobility with African resources and technologies, where we talk about bringing research to reality. We have had so many episodes, and this one I also promise us that it will be good and insight insightful. Sorry. So I have with me here Professor Greg Natara, a professor who needs no much introduction. His works and legacies says much about him. He's a professor who has done a lot in the field of engineering. Uh, so I will just have to say a little about him because his legacies can't actually be talked about. He has done many things, and we are so happy and elated to have him here. So Professor Greg Nasara is a professor in the Faculty of Sustainable Design Engineering and former Vice President, Academic and Research at the University of Prince Edward Island. Previously, he was the Dean of Engineering and Applied Science at Memorial University of Newfoundland. He had some significant research contributions to energy systems, heat transfer and thermodynamics, including 3 books, 6 patents, and numerous referred articles in this field. As a former Taiwan Canada research chair in advanced energy systems, he led an international research network on the development of new hydrogen energy technologies. Professor Nassar received the Julian C. Smith Medal of the Engineering Institute of Canada, EIC, for exceptional contributions to Canada through engineering. He was awarded the Innovative Achievement Award for Research Ingenuity by the Canadian Nuclear Society, NSC, and the Jules Statues Medal of the Canadian Society for Mechanical Engineering, CSME, for outstanding contributions to heat transfer. Professor Nassar was inducted as a fellow of several engineering societies and institutes, CSME, ASME, EIC, CAE, and AIAA. Professor Nassar had held prominent national leadership roles in higher education and research, including as Chair Engineering Deans Canada, formerly the National Council of Deans of Engineering and Applied Science. He is the editor-in-chief of the Journal of Thermophysics and Heat Transfer of AIAA, that is American Institute of Aeronautics and Astronautics. Professor Natar received his BMAS, that is Applied Mathematics, uh, Mechanical Engineering, and PhD degrees from the University of Waterloo. So he's a prominent professor who, when we mention the likes of pioneering engineers like the likes of Nikola Tesla and all, so he's one of those who keeps the wheel of engineering rolling, and his contribution so far has had many impacts in the field of engineering, and we are so happy and so uh, we are so happy to have you here, sir. We are so happy. So we'll be taking us on the topic hydrogen energy fueling clean future. hydrogen energy fueling clean future. So I will urge each and every one of us here to bring out our notes and our brain to, because it's much like we are in class now. So Professor, sir, over to you, sir.
Well, thank you very much for that kind introduction. It's very much appreciated. It's a pleasure to be with all of you this morning from Charlottetown, Canada, and from your side, it's in the afternoon. You're some hours ahead of us here. It's a beautiful day in Charlottetown, PEI, and I'd like to begin again by thanking you for the introduction, and also just start by saying that I've had the pleasure over many years to have the opportunity of supervising outstanding graduate students and PhD students, including one who is, you all know, Dr. Emmanuel Ogadengbe, who was just a pleasure working with Emmanuel, and I'm so delighted to support him and this initiative that he's leading and the work that he's doing. So I do have a presentation. I'd like to speak about hydrogen today. So if you give me a moment to pause and to share my screen, I hope this will come up correctly. Okay, can you see this correct? Good? Is this good?
Yes, sir. Yes, sir.
Okay, very good. Okay, so I have about 30 slides here, and I understand I have about 30 minutes. So please just stop me if I'm going over time here. I'd like to talk about hydrogen energy fueling a clean future as part of this SMART research initiative. As mentioned, I'm Greg Natterer. I'm a professor, former vice president, academic and research at the University of Prince Edward Island in beautiful PEI, Canada. So here are the topics that I'll speak about today. First, it's going to be all about hydrogen as a clean fuel. So the usage of hydrogen, the methods of producing it. I'm going to focus on one in particular that is a uniquely Canadian technology, and one that I had the opportunity of leading a team over many years in developing. It's called the copper chlorine cycle. Hydrogen storage, a bright hydrogen future, and acknowledgements. I would really welcome and enjoy hearing any of your feedback during my presentation. So please just interject when I'm speaking. First, a little commercial break. Just take a pause for a moment and tell you about a couple of things going on from my side. I am proud to have this textbook that is widely used around the world. It's called Advanced Heat Transfer, suitable for both undergraduate and graduate levels. It has a third edition that came out, but a new fourth edition will be coming this fall. So look for that if you have an interest in this subject of engineering heat transfer. The book covers a wide range of topics in both single phase and multi-phase heat transfer. And so just to let everyone know, a fourth edition is coming this fall. And also, as mentioned, if you have research publications related to thermophysics or heat transfer, I'd encourage you to consider submitting to this journal, where I am the editor-in-chief. It's the Journal of Thermophysics and Heat Transfer of the American Institute of Aeronautics and Astronautics. Okay, moving on to hydrogen. Hydrogen is a promising clean energy carrier of the future and a potentially major solution to the world's problems of climate change and greenhouse gas warming. It can be produced in a clean manner, and when done so, its combustion produces no CO2 and just water vapor. So a lot has been talked about with hydrogen in regards to transportation, in fuels and vehicles and so on. But actually, hydrogen is widely used in many industries already today at a large scale. So this is just a diagram showing you some of them. In the upper left, hydrogen is used for upgrading of bitumen and other petrochemicals to synthetic crude oil, and is used, it's a critical component and feedstock for the refining of petrochemicals to higher grade fuels. Just going in a counterclockwise direction, I suppose, it can be just going around in the images there. It can be used in boilers and fireplaces and residential applications in place of fossil fuels. In industrial processes like metallurgical and the reduction processes of production of nickel and other metals, hydrogen is widely used there. And hydrogen is a promising clean fuel in the transportation sector. So there have been conceptual designs and significant work done by aerospace companies in the use of hydrogen as a potential future fuel in aviation. So hydrogen has some pros and cons as a fuel in comparison to kerosene. It has about 4 times the requires about 4 times the volume to carry the same amount of fuel to cover a given distance by an aircraft. So that's a disadvantage. But on the other hand, as an advantage, it carries about 3 times the energy density as a liquid fuel. So it has 3 times the gravimetric energy density as a fuel, but 4 times lower as a volumetric density compared to kerosene. So those almost offset each other in a way. So as a liquid fuel stored on aircraft, hydrogen has, I think, very significant promising potential. It's also used widely in the production of fertilizer and ammonia. So hydrogen is necessary for food production in the world today in large quantities. A lot of work going on in hydrogen in other modes of transportation like ships and trains. So this is an example of a train in Japan running on hydrogen. And also, of course, we've heard about hydrogen fuel cell vehicles, and still significant investment by automakers around the world in hydrogen. The electric vehicle batteries are very promising as well, but I think hydrogen has some unique advantages when it comes to longer range and for heavy-duty trucks and transport trucks and the like. So it will, I think, play a part of the transportation future. So how is hydrogen produced in the world today? Hydrogen doesn't exist naturally in nature the way fossil fuels do. So it needs to be produced or manufactured somehow. And what are the primary sources of hydrogen? Well, there's 2. One is that hydrogen is contained within fossil fuels like natural gas, coal, and others. So one of the primary technology in the world now for producing hydrogen is reformation of fossil fuels like natural gas. So it's 96% of hydrogen production in the world, but that has some disadvantages. Of course, it has air pollution, CO2 emissions, and potential future of increasing carbon taxes and the costs of sequestration. Another alternative is electrolysis, which produces hydrogen instead from water. So there's an abundance of water that we have, but a disadvantage here with electrolysis is that it has lower efficiency and higher costs because it's using electricity to split the water. Are there any other alternatives that are promising large scale and lower costs? Well, potentially. I'm going to go through some slides quickly here on some research that myself and my team have done over the years. And very quickly, if you have any questions as we go along, again, please don't hesitate to interrupt. So solar energy with the use of photocatalysts and water is a promising technology that is being developed at the laboratory scale. Essentially, the way this works is that photocatalysts, which are like nanoparticles immersed in water, can absorb sunlight and through that absorption process generate a reaction that splits the water into hydrogen and oxygen. I'm working from home today, so I apologize if you hear a dog barking in the background. He's been misbehaving lately, so just please ignore that. Another method of water splitting is thermochemical processes. So what happens here is that if we consider the splitting of water to produce hydrogen and oxygen, if you try to do that directly, it requires very high temperatures to split steam into hydrogen and oxygen, thousands of degrees Celsius, which is impractical and difficult to obtain such high temperature heat sources, and rather inefficient. So another promising technology is the use of intermediate chemical compounds that reduce the temperature and can split the water at low temperatures while recycling all of those intermediate compounds. Two examples are the sulfur-based cycle and the copper-chlorine cycle. These are being developed largely in connection with next-generation nuclear reactors that will produce both hydrogen and electricity. Sulfur-based cycle has been developed extensively, including at the pilot plant level in Japan and some other countries. Disadvantage is the very high temperature that it requires, about 850 degrees. An alternative, which is a uniquely Canadian technology, is called a copper-chlorine cycle. I'm going to talk about this now for the next little while. I led an international team in partnership with Canadian Nuclear Labs on the development of this thermochemical process. If temperatures available are not high enough to supply the cycle with a maximum temperature of 500 degrees, there is a technology called chemical heat pumps, which can use waste heat from industrial or other sources and be boosted up to higher temperatures through a sequence of endothermic and exothermic reactions. These are called chemical heat pumps. They are similar to regular heat pumps and refrigeration cycles that we know about, except that they use, rather than a pressure volume changes, they use chemical reactions that elevate the temperature of the process. So this is the copper chlorine cycle. My team and I have developed several patents around this. Essentially, it's 4 processes: thermolysis, hydrolysis, electrolysis, and water separation through a crystallizer or other method that essentially splits water into hydrogen and oxygen, as you can see here. So I'm going to go through several slides now that show that we've developed our team some few years ago in collaboration with Ontario Tech University, Canadian Nuclear Labs, and others developed the world's first large-scale demonstration of these unit operations, and in fact, an integrated cycle as well. So it's, again, the 4 processes are shown here, and I'm just showing the portions of heat input to the cycle. Okay, and an integrated cycle that was developed in the laboratory, showing the different components. And essentially, again, just to repeat, the only input to this process is water and some electricity, and the outputs are hydrogen and oxygen. This is a conceptual layout of the integrated cycle from the previous slide. So just a couple of highlights of it. It's an integration of thermolysis and hydrolysis units that produces 50 liters per hour of hydrogen. Hydrolysis reactor consists of a 5-foot tall tube with a barrette-like injector of copper chloride 2, separation by selective distillation in water, and auxiliary units that perform the fractional distillation and the pressure swing processes within this cycle. Okay, so I'm going to just go through each of the processes. There's a copper chloride HCl electrolysis process that requires much less electricity than does water electrolysis. This is one of the steps in the hybrid cycle. These are results that were produced from the industry partner that we had, Canadian Nuclear Laboratories, that show continuous operation of the electrolyzer over many hours. Following the electrolysis process, there needs to be a separation of the water from the copper chloride 2. So a crystallization process is done there. This is just showing some images and schematic of the process. It's a binary system at saturation. 20% of the CuCl2 can be crystallized in a matter of hours, and these dendritic crystals are formed in the range of 0.1 to 0.6 centimeters. So this is a slide showing the sequential steps of crystallization from the point of where it initially appears, growing denser after the solution is removed and after crystals are formed. So what happens here is that this water needs to be removed because these crystals are then transported and as feedstock for the hydrolysis reaction, which is the intermediate step that reacts with steam to produce copper oxychloride as one of the 4 steps that I mentioned. Alternatively, other than crystallization, it is possible to do a drying process, and this is an experimental facility that did this. This is a spray drying of the copper 2 chloride solution, and in this process, the slurry progressively dries, and you see here the stages for surface drying. A crust is formed, bubble nucleation, a crust is collected, and there's a final solid particle at the end in a spray drying process. Hydrolysis is the process that I mentioned where this dried particles are then injected into. This is the experimental setup here, showing, by the way, this is each of these slides here, I can be glad to provide references to some journal papers. This is work done with Dr. Kevin Pope and myself during his PhD thesis on demonstration of the hydrolysis process. And just some sample results from the hydrolysis reactor showing the excess steam requirements at different temperatures, and the XRD pattern of the solid particles showing the chemical composition. One of the challenges with the cycle is that there are side reactions and byproducts that need to be handled in the cycle. When the HCl and steam mixture exits the hydrolysis reactor, those two need to be separated. And the separation of HCl from H2O is done by means of partial condensation and recycling of the products. So there is a azeotrope actually that happens here for this particular mixture, which makes it more difficult. So the condensation needs to be done in several sequential steps, as shown in this figure. And the experimental work was done in this process too, to demonstrate the separation of the two. Okay, then there is a thermolysis. I think this is the last one that I'm going to show. This is a process that takes the product from the hydrolysis reaction. It's a copper oxychloride. It then decomposes in a molten copper chloride salt, and releases oxygen, and then the liquid that is then produced, the copper chloride, is cooled, and that goes back to the electrolyzer to complete the cycle. Studies were done on how to improve the efficiency of these reactors. So this is a study done by Brodeurs and others, and myself, on staging the injection of steam at multiple points to reduce the total steam consumption. So this is showing the exiting solid stream from the reactor supplies the next stage, where fresh stream enters, gas is recirculated, and there is iteration until all of the CuCl2 or steam is fully recovered. Okay, this is just a schematic of the hydrolysis reactor. It's a tube furnace, as you can see here, where a crucible and the molten salt are placed, and the solid is decomposed. And some modeling and analysis was done of this process. So here we have a solid particle that is decomposing in a molten salt that releases oxygen gas. So there's a lot of complicated transport phenomena going on here, an outward moving phase interface, oxygen bubbles that are produced, and thermal resistance that dominates the phenomena. Once the molten salt is produced from the thermolysis, we need to recover heat to uphold the thermal efficiency of the cycle. And this study here is showing heat recovery from molten CuCl droplets falling in a quench bath, as well as X-ray diffraction of the quench product, showing that the molten CuCl does not react while it's in the water. Okay, that's it for the copper chlorine cycle. What is the future vision for this? Well, colleagues and myself have been actively seeking out future industrial receptors to further scale up this technology to an industrial pilot plant. And that's what has happened here, is that small test tubes have demonstrated the viability of the cycle at a very small scale. Actually, this was done originally by the Argonne National Lab in the United States about in the early 2000s. And since that time, my team and I have developed large-scale lab engineering equipment at the scale of about 5 kilometers per day, kilograms per day, sorry. And the testing continues, and the research is ongoing. The next stage, though, is that we are aiming to partner with an industry receptor, such as one that produces waste heat at high temperatures, like a steel plant or a cement plant or other heavy chemical production or furnace companies that have high temperature furnaces that release some waste heat, to partner with them to utilize that waste heat and produce a pilot plant. After a pilot plant is demonstrated, then the next would be large commercial plants that in the future could potentially be linked with nuclear plants or with solar plants or, again, other industrial manufacturing facilities. This is just a schematic showing of how the cycle could be linked with a nuclear power plant with the 4 steps in the cycle. And really the connection is input heat through an intermediate heat exchanger between a nuclear plant and a hydrogen plant, carrying heat in the form of high temperature steam that supplies the thermolysis reactor. Also, waste heat from the nuclear power plant can be used towards the first and second steps, particularly the water separation. So that's again a unique advantage of this cycle that can utilize waste heat. So hydrogen as a storage medium. For nuclear energy, when prices, there's daily price fluctuations based on supply and demand of electricity. And when periods of low demand and low price, a potential option for power plants is the storage of that electricity in the form of hydrogen. Also, for renewable energy like wind and solar, at times when the wind is not blowing and the sun is not shining, there needs to be energy storage to have a more consistent power output. And hydrogen is a potentially promising form of energy storage that can store electricity during periods of low demand and price, and then convert it back to electricity via fuel cells, for example, or direct combustion engines when the demand is high. So again, hydrogen storage would be a promising way to address intermittency of wind and solar energy. Past study was done that compared the economics of a thermochemical cycle with electrolysis. I'm not going to go into the details of all of this here, but essentially what it's showing with the figures in the right side is that at larger hydrogen scales with a thermochemical hydrogen plant, under some assumptions, the economics become increasingly attractive as the scale of hydrogen production increases. And so this is a potential bright future for hydrogen, that you would have a source of energy. It could be nuclear, could be solar, could be other waste heat from industries, as I mentioned. That electricity and heat could go into the water splitting with a thermochemical cycle or electrolysis, and then that hydrogen, as well as oxygen, actually is of value for industrial users and also for our homes as a transportation fuel and many other forms of usage, as I described earlier in my presentation. And I'd just like to acknowledge the various partners and collaborators at these organizations that I've had over the years and were part of the work, significant part of the work that went into the slides that I showed. So thank you for your attention, and I'm going to stop sharing now.
Okay, thank you. Thank you very much, Professor Greg Nadra. And before I allow the moderator to go ahead and invite questions, I just want to say thank you very much from myself. I thank you for also letting the audience know that you have a very huge impact in my life. Professionally, I can always remember the very first day that I met Greg Nadra in his office. I just landed in Winnipeg over the weekend, from almost plus 30 degrees to minus 30 degrees in December. And happy to see my new supervisor. And the first greeting that he had for me was to walk me through to the bookstore at the University Center. And I was like, when you go there, you see a lot of shops and restaurants. I was thinking maybe he wants to offer me coffee. And the first thing he got for me was a Visual Studio package for my baptism into programming. That was, I can't forget exactly that very gift. I still keep that very studio, that very package. At those times, these are the days when you just go now online and you just download Visual Studios. In those days, you have to buy the kit, and I still keep that kit in my shelf, even in the office at the University of Lagos. Still there. I can't really actually forget that. So I want to really appreciate that baptism into the world of programming with C++, because while in Nigeria then I was only able to use Fortran 77. I believe these days people hardly know what Fortran 77 is, so that was what that was what everybody was using, but then C++ came forward and then everything changes. So it's been a very wonderful time, in the field of computational fluid dynamics and all that I've achieved over the years. Thank you very much. Now, just looking at the presentation today, I was just trying to look at how hydrogen energy can actually partner with what we are doing as SMART. And what I can take out of the presentation is possibly that this is a technology that is more attractive to economy that have sufficient energy, because you will need huge waste heat for the water splitting. You will need industries that have a lot of energy sufficiency, and their concern is just how to store energy. But that is not the concern of Africans. We're looking at energy that is not enough. We want to really have enough before we can be talking about storage. So hydrogen energy product as presently the work that you've done at lab scale and looking at pilot scales would be more amenable to the African cities, particularly what SMART is concerned about is how to deploy electric vehicles, how to make electric vehicles very much, adaptable, given that we have problem of energy reliability. So we don't want the operation of electric vehicles, or as your technology concerns now, transportation driven by hydrogen energy. We don't want it to depend on the already unreliable grid that we have. So there must be an off-grid, way of producing the hydrogen energy. So presently what you have now, how can it be adapted in such a way that maybe at a very small scale, residential, commercial home users can have a means of accessing this hydrogen fuel without any negative impact on the national grid? So that is what is going to really be more attractive to what we do at SMART. So I just wanted to speak a little bit more on that before we have the moderator take over with questions from the audience. Thank you, sir.
Thank you, Emmanuel. That's a very, very interesting story about when we first met. Yes, times have changed with software. So again, I have many fond memories of working with you, and you did outstanding work when you were at the University of Manitoba. So would you like me just to say something about like the hydrogen and in African countries and the waste heat, like what you were talking about, or should we open it up for other questions?
Yes, you go ahead with how that hydrogen energy can be, applicable to the context of African countries.
Yeah, I think so. Solar energy, I would say, is a potential, and the solar photocatalytics. So concentrated solar energy to provide the heat input to drive the process. But I agree with you that this is really not, the copper chlorine cycle is still at a relatively low technology readiness level, because it needs to partner with like some form of industrial plant. But I do think that other uses of hydrogen, such as electrolysis or renewable energy, solar energy, linking it with that, have some potential. But I'd be glad to explore those different venues with you, Emmanuel, and your group. But it's still in a development stage around the world, and potentially as a fuel for ships that are in the coming offshore. Not sure. Areas that we could explore for sure.
Okay. Thank you very much. So we'll look forward to that, and the students are all here, and we'll talk more. I know we've been actually talking about a lot of collaborations and how students can move to PEI, for close supervisions and all that. But we'll definitely go on as we have started in the past. So moderator, over to you, please.
Thank you so much, Professor Sir. Thank you so much. Really appreciate the enlightenment and Dr. Gedende for that wonderful question. Because as a student, while following what Professor was saying, we were like, okay, what would be the application to Africa? And as an undergraduate, you have a lot of questions. I know my fellow audience here will have a lot of questions, and I know we will also want to go and watch this all over again. And each slide needs much breakdown for undergraduates like us. So as doctors, so you can assimilate more. But we as an undergraduate, we have to take each slide and be like, okay, what does this mean? What does this mean? And I know we actually appreciate Professor Sir. Now I will entertain questions from the audience. Anyone who have question. And before then, as the doctor mentioned, your impact, sir, Professor Greg, is no more in news, because even the day we posted the flyer that we inviting you, someone already mentioned that, wow, are we big prof? He was the one who supervised his masters and all. So it's your legacies are already around the world, and we really appreciate you for the job well done, sir. May the Almighty always be with you and prolong your life. So anyone with question here from the audience? Anyone with question for?
Now the hands are already on. You can just
Okay.
maybe give them the floor one after the other.
Okay. Kehinde Olaitan. So just unmute.
Good afternoon, Professor Greg.
Hi.
Good afternoon. Good morning. I know it's morning over there. Yeah,
Yes.
in fact, for the first time, I'm so glad talking to you, because I know you don't know me. You don't know me, but me, I know you very well, even if not physically. Yeah.
Wonderful.
Yeah, because I remembered my first paper that I published with Professor Gidingbe, my supervisor. You are co-author on extension of Nisos to try quadratic. I don't know if you remember.
Yes, of course, of course.
Yeah, that was my master's work.
Oh,
Yeah,
excellent.
my master's research. Yeah, and in fact, sincerely, after then, I think I told my supervisor, I told him that I have been trying to connect with you. I want to talk to you, but all my efforts were futile. It's not a problem. Yeah, were futile. And later I saw the post that they were bringing Professor Greg Natera. In fact, I was just so happy. I said, cool. In fact, I'm so glad.
Oh, yes. I'm also delighted to meet you. Yeah, that was a good work, and so happy to meet you as well.
Yeah. Secondly, I followed your presentation, and what I'm so concerned actually about is how this can be applicable to Nigeria, because Nigeria presently, what we have been, the talk of the day and the research of the day is on solar energy, wind energy, but how can we also harness this opportunity, you understand, for energy generation and storage in the country? And let us see how, because the solar energy has its own limitation. It will be bogus if you want to use it to generate large amounts of energy for industry, which I know hydrogen energy is capable of. So how can this technology be, how will I put it, be encouraged, be researched, and also fit for Nigeria application? That's one of my.
That's a very good question. And I think Emmanuel asked something similar as well. So here is one possibility for you to think about. You mentioned that there is use of some solar energy in Nigeria, right? So here is, so solar energy presumably for electricity production, for example, photovoltaic. Now, when you take the energy spectrum of solar energy, there is a portion of that spectrum that goes into the electricity production process through the photovoltaics. But there is an unused part of the spectrum that doesn't go into that productive photovoltaic electricity production. My team and I have done some work where you can use that unused portion of that spectrum to produce hydrogen, right? So using photocatalysts in water, Okay, so what that means is that you can have the current solar energy technology that you have, but there is essentially an unused or a wasted portion of that spectrum that is not going into electricity production. You can then couple it or have a hybrid system that is using some of the spectrum for electricity and the remainder for hydrogen production through photocatalytic means. So that's something that I think is potential, just an idea.
Yeah. Okay, I will talk to Professor Gedende on this, and because it's something I would really like to work on, coupled with the fact that I just finished my PhD in Nigeria. Yes.
So this process that I just mentioned is not the copper chlorine cycle, right? Do you remember I had one slide near the beginning that was, I went through quickly, solar photovoltaic. If you look at that paper, you can combine both solar voltaic for cogeneration of electricity and hydrogen, which I think could be relevant in Nigeria.
Yes.
Okay.
Thank you very much, Prof. I will talk to Professor Gedende, and I will see how we can collaborate actually. And I also hope you are not yet preparing to retire anyway.
Oh, pardon me?
He was asking if you are not too close to retiring from academics.
Oh, have you heard there's a saying that we have here? It's I think it's kind of true, is that engineers never retire. Even when they stop their work at the university, they're still doing research, they're still thinking about engineering, right? I know many colleagues who have retired and they're still continuing doing one form of engineering project or another.
Okay, thank you very much, Prof. Yes,
Thank you very
let's
much.
have a moderator the next.
Yeah, thank you so much, sir. Thank you so much. So, Odunayo, you can go on.
Hi there.
Smart conference, Odunayo.
All right, thank you very much, sir. Really appreciate your input thus far. It has been an insightful one. We so much appreciate you. On my end, one thing that you actually brought to my mind was when you mentioned the fact that there's clean hydrogen. So that led me to even like, okay, thought of it that then we should have like a gray hydrogen in terms of categorization. I noticed that they categorize it in terms of clean hydrogen and then the gray hydrogen in terms of the energy production, how will I put it, source, energy production source. So as you've mentioned, the waste heat is a form of clean energy source. And for a country like Nigeria, it means that then we have to have like enough waste, what's it called, enough waste heat in place for us to even think about taking the trend of hydrogen production. One, enough waste heat. And then the next question, when you mentioned the volume disadvantage, that's in terms of storing hydrogen and trying to utilize it per time, the volume disadvantage is one thing that poses a challenge also. So I'd like to ask if there are research in the part of solving the volume disadvantage. That's my first question. And then in terms of waste heat provision, for a country like ours, which we categorize as developing, I do not know whether we have enough heat sufficiency yet in terms of waste heat. Although from my last listening to Aliko Dangote, I had him mentioning the fact that they utilize a lot of water in cooling their machineries and all of those things, which could have been diverted into hydrogen production, I believe, if it's actually opportune to listen to this type of webinar, rather than trying to consume water in cooling their or in in how will I put it? Energy cannot be destroyed, right? But it in a way can be distributed. So rather than trying to use water in distribution, is they can actually implement it in hydrogen production. So that's my next question. Like, as a country like Nigeria, should we look into building more industries so as to have more waste heat available, or are there other means of sourcing it that are not so expensive. So sorry. Hope you got my question, sir.
Good questions. Thank you, Adebayo. You had a few questions there, and I'll go with the first one around the volume disadvantage. And you are right. There is, as I mentioned with the aircraft, the volumetric density is lower per unit content of energy of a fuel, which means that the storage tanks are larger for liquid hydrogen on a plane, but the gravimetric or the mass density is higher. So that means that for a given mass of hydrogen and another fuel, you're going to have much more energy content in liquid hydrogen, 3 times more. So what can be done about this? Nothing really, right? Because these are thermophysical properties of different fuels that we can't change. But what we can do is develop the suitable hydrogen storage technologies that will enable the hydrogen to be used. So there are different storage technologies like metal hydrides and high pressure storage of hydrogen as a gas or cryogenic storage. But there's also other intermediate hydrogen carriers like ammonia or methanol that can be used to store hydrogen in a way as a liquid at room temperature and then easily evolve it during its application. So they're intermediate hydrogen carriers. So that's another alternative. And then your question about the waste heat. So in that situation where waste heat isn't available, I think there are other heat sources that can be made available. It doesn't require just waste heat. It could be like, for example, solar energy. So solar heat, solar collectors that concentrate solar energy into a thermal reservoir. Then you have a high temperature thermal liquid that is storing solar energy that can be used as the high temperature heat source. It doesn't have to be waste heat. So those are some alternatives that could work.
Thank you. Thank you
Okay.
so
Thank you, sir.
much, sir.
Thank
But
you, sir.
are you
I
are you
just want to
satisfied? Okay.
Very well. I just want to add one more thing, which is very important as per my thoughts, is that last I heard about hydrogen was in form of trying to, I don't know, I'm an like explorer of some sort, in form of like during the World War trying to create like an hydrogen bomb of some sort. So that brings to my mind that hydrogen can be somewhat pose some threat in terms of when it is not well managed, right? So around the research and around the storage and utilization of hydrogen, I would like to ask if we've looked into the dangers that its implementation might pose, and if solutions are being, or if how would I put it, the machineries, if they are being like created around curbing any danger that hydrogen utilization as a source of energy might pose. So that's my last question. Thank you, sir.
Yeah, that's another important area of research. A lot of work is going on in that area. Hydrogen safety. You're right. It does require changes to codes and regulations when hydrogen is used as a fuel. But industrial gases like natural gas and others have been used for a long time, and industry currently uses hydrogen at a very large scale in many different applications. So I think the technologies are well known to deal with hydrogen safely. It's just that it would require differences in terms of materials and components and other aspects depending on the application it is. So I think I don't think I don't think this is an area that should prevent us from using hydrogen at a larger scale, because it's. But having said that, more research does need to be done on hydrogen safety.
All right. Thank you very, very much, sir. I really appreciate your responses. Thank you, sir.
Thank you so much, sir. And the last question from please go on.
My apologies.
Thank you very much.
I couldn't hear
Oh.
that. Sorry, the signal.
I don't
It's
think
not
he or
good.
she can hear me. Because, I would like our honorable doctor give us a closing remark.
No, we still have Adebayo Omiri instead there, putting up his hand.
Yeah.
Sorry,
Okay.
can you hear me now?
Yeah, we can hear you now. Please go on.
Okay. Thank you, Professor Greg, for the lecture. I'll
Yeah.
keep my question brief. So it comes in stages. I want to know your informed perspective on, especially the concerns like the technological bottlenecks. As we know, hydrogen is famously difficult to handle and can be very hazardous. So, like, what would it take for mass adoption in the market? You mentioned at some point that you are looking towards running experiments at an industrial scale. So that also now brings into question commercial viability and funding. What level of progress do you think has to be made right now that would pull investors into the field? And like, what field as a lead researcher is it best for the world to focus on to make hydrogen energy viable?
That's a great question. And my colleagues and I have published a couple of articles in the past year that are in two journals. One is Fuels, and the other is a journal, I think it's a Canadian Journal of Chemical Engineering. And those two papers give a very detailed answer to what you just asked there. I would encourage you to take a look at those. I'd be glad to send you a copy if you'd like. Those papers provide a comprehensive review of hydrogen landscape across Canada in particular, but also internationally, and all the aspects of hydrogen, from the bottlenecks and challenges and opportunities in production, in usage, policy, regulatory framework, storage, all of these elements. And it's showing that there is a lot of work going on and a lot of significant progress in those areas. So, that's where I would point you to, that really has, and it's a recent article. It was just published this year, two of them, 2026, very detailed review articles.
Thank you, sir. I would appreciate the articles. I would like to go through them.
Yes.
Okay. Thank you very much, Professor Greg Nadra. And I want to say, yes, you promised the two articles for the sake of members of this very webinar, and also members in the WhatsApp platform that we have for SMART. We would like to post those two articles there for them to access, and then Adebayo can fetch it from there. So I will remind you to send the articles to me, and then I will post it on the platform for everybody to be able to review that. So once again, I want to appreciate your time and your collaboration with me over the years, and also with this SMART initiative. And I look forward to more collaboration. I've seen some of the past students also that have signified interest in working with you, and we'll see how the collaboration we proceed in the upcoming years. To get some of them possibly to PEI to co-supervise with you, and then also advance what we are doing at SMART. And I just also want to inform the audience that Greg is very much delighted in SMART. Since last year, he made a presentation at his launching last October, and he also joined the editorial board of SMART. And I am so delighted anytime I see him around me. I feel safe. I feel, that I'm on the right path. So thank you very much for your continued collaboration. So before we close, I want to also thank everyone, that have joined in the presentation today. We are running up this series of From Research to Reality today. We will start a new series next week. And the series we are starting is focused on energy management. So there will be a couple of guests that will be coming up to speak to us on energy management, and possibly, just as we started from research to reality with me, opening the floor, I and maybe some of my associates will come up with something to introduce energy management next week, if I can lay hold on somebody from outside. But anyway, we've done significant work on energy management that we want to open the floor on what we expect the participant to see in the series. And then after that, next week, the upper week, we already have a very renowned expert has already taken the slot for August 14 that will be speaking to us. But we always want to make the very first presentation in the series something like introduction to the subject matter. So prepare, and join us. And those, because this period of 2 p.m. Nigerian time is always the working hour. Most of people that are in the platform have always want to join the presentation online. So this is live stream. So on YouTube, you are welcome to catch up if you have missed anything during the presentation. So once again, thank you very much, Greg Nathra, and I want to also appreciate the management team, of interns of the Energies Research Group. So over to you, moderator, to round up. Thank you very much.
Yeah, thank you so much, Honorable Doctor, person of Dr. Emmanuel Gedende, for that wonderful remark. And we appreciate every one of us here, starting from Professor Greg, and to every one of us who have been following the SMART conference from the beginning till now. So, and we promise will also be a great of us here, and we say a very nice goodbye. Bye.
Bye.
Bye-bye.